Hi Prof, my name is Zijin, and today I'll be presenting my final year project, Music Generation with Deep Learning Techniques. This is a summary of the content I'll be going through. Firstly, I'll give an introduction to the topic of my project, Music Generation with Deep Learning. Before I get into the technical details, what is music generation? It is a computer-based generation of music using machine learning algorithms. Recent interest and development in artificial intelligence spurred researchers to explore the role machine learning could play in creative sectors such as music, specifically in the process of music generation. There are two main objectives in computer-based music generation. Firstly, to create original music using autonomous systems for various purposes such as commercials, games, documentaries. And secondly, to serve as a tool to assist musicians in composing, arranging, or producing. Now that we have an idea what music generation is, what is deep learning, and what makes it suitable for generating music? Deep learning is a subset of machine learning methods that uses artificial neural networks for both supervised and unsupervised learning. The term deep refers to the multiple processing layers in an artificial neural network that progressively extract higher level features from raw data. So, why deep learning? The motivation behind using it to generate music lies in its ability to generalize learning. Its automatic learning of different musical styles and patterns from music corpora allows it to generate new music based on the learned sequences and patterns. Next, let's look at the different aspects of a deep learning music generation system and review some state-of-the-art implementations. There are three dimensions to a deep learning music generation system: objective, representation, and architecture. Objective refers to the type of music generated and use cases the system is designed for. Representation refers to the format in which music can be processed and encoded as data. And architecture refers to the neural network's composition of neuron layers and connections. For the purpose of this presentation, I'll be zooming in on a specific section of representation, as well as the architecture of deep learning music generation systems. Under representation, there is a segment called temporal scope representation, which is essentially how time is represented in a music generation system. Music is essentially a sequence of notes, and it is the time pattern between notes that gives rise to meter and tempo in music. Meter is the rhythmic pattern formed by a group of notes and is specified by a time signature, while tempo determines the speed of the music. In this example, the time signature is 4/4, which means that there are 4 beats in a bar, and there are 120 beats per minute. Therefore, in a music generation system, meter and tempo are encoded by the system's temporal scope representation, which determines how music is processed and generated with respect to time. There are three types of temporal scope representation. Firstly, there's global step, where an entire musical piece is seen as a single processing step, and thus the system generates the entire piece in one step. Secondly, time step, where each processing step in a system corresponds to a specific time step in the music, and the system generates the music in successions of time steps. Lastly, note step, where each processing step corresponds to a single note of any duration, and the system generates the music in successions of notes. Time step is the most commonly used representation, and a single time step is usually set as the smallest duration of a note in the dataset. Moving on to the architecture of deep learning music generation systems. There are many different types of architecture that machine learning engineers have used to build music generation systems with. It ranges from the simple feed-forward network to the novel and recent generative adversarial network. A comprehensive review of different types of architecture can be found in the report. And for this presentation, I will be zooming in to the recurrent neural network, also known as RNN, and the bidirectional RNN. A recurrent neural network is a feed-forward neural network that feeds the output of each hidden layer back into the same layer as an additional input. Every node in the hidden layer receives output from the previous layer and current layer in the previous time step. Thus, the RNN is suitable for learning timed sequences. Given that music is made up of timed note sequences, RNN is commonly used as an effective architecture for music generation. However, RNN suffers from the vanishing and exploding gradient problem due to its repetitive multiplication of the recurrent weight matrix in backpropagation. The solutions to this problem are the long short-term memory, LSTM, and more recently the gated recurrent units, GRU. Both LSTM and GRU have a similar recurrent input flow as RNN, but differ in their logic gates that identify and remember important features in a sequence. This mitigates the problem of short-term memory in RNN and allows the network to persist meaningful data across sequences. I will be focusing on the LSTM architecture. This is a graphic depicting the operations within an LSTM node. The cell state contains information that gets passed down the sequence and goes through logic gates to add important and remove irrelevant information. The forget gate determines the information to discard from the previous hidden state and current input. The input gate decides what information to keep from the previous hidden state and the current input, and the output gate delivers the next hidden state. Let's look at an existing music generation system that uses a LSTM network. Machine learning engineer Sigurður Skáli built a music generation system called Classical Piano Composer. It was trained on a dataset of Final Fantasy soundtracks and used to generate original music in the same texture and style. A typical song from its soundtrack sounds like this. The model is made up of 3 layers of LSTM network with 512 neurons with categorical cross-entropy as its associated cost function. Let's listen to a sample of music generated by this system. The generated music makes melodic and harmonic sense and are reminiscent of the Final Fantasy soundtracks. This indicates a potential in generating music with a LSTM network, especially given its ability to learn important harmonic features of the style it is trained on. However, this current implementation is only able to generate notes of a fixed time step and is unable to process notes that are not initially found in a dataset. Next, let's look at another architecture, bidirectional RNN. The bidirectional RNN is made up of one RNN that starts at the beginning of a sequence and flows forward in time, and another symmetric RNN that starts at the end of the sequence and flows backward in time. It makes predictions based on sequences before and after the current element. Bidirectional LSTM chord accompaniment symbolic music generation system uses a bidirectional LSTM network of 128 neurons. It was trained on 1,802 songs and generates chord progression for a 4-bar melody. In comparison to other machine learning models, the bidirectional LSTM has better accuracy and received more positive feedback from a user survey. It also generated more variation. Through the analysis of current literature, some potential directions for further research were identified. One interesting design decision to consider is temporal scope. Current temporal scope representations lack content variability as they are only able to generate a fixed length or fixed time step, resulting in regular meters. However, the progression of musical styles has shown an increase in the use of and preference for irregular meters that cannot be generated with current temporal scope representations. RNN's ability to remember and learn information from previous time states makes it a suitable network for the task of music generation. Bidirectional RNN creates further room for research as the relationship between the network's backward time analysis and the generation of coherent musical content can be investigated. Therefore, the project's hypothesis was developed. Based on a research direction previously identified, a new temporal scope representation that is a hybrid of time step and note step was proposed to generate irregular meters. A network made up of bidirectional LSTM layers was hypothesized to be able to better capture and generate musical sequences. Next, I'll go through the design and implementation of this project's music generation system. The project's design is split into three dimensions: objective, representation, and architecture. The project's implementation is also split into training phase and generation phase. I will first be going through the design. The high-level objective of this project is to develop a deep learning music generation system that generates music with irregular meters and improved coherence. Single voice polyphony was chosen as the type of content to generate, as harmony in polyphonic music is important for evaluating the model's success at learning and generating sequences of musical value. The system was designed to output MIDI files, as music can be analyzed more objectively in symbolic representation. MIDI files also include useful information such as pitch, duration, and offset of each note. The system was designed to be mostly autonomous, with some level of human intervention such as the length of music to be generated. Ragtime, an American musical style, was chosen to be the style of the music generated. Its strong rhythmic characteristics make it suitable for the hypothesis, as it could be determined if the proposed hybrid temporal scope allows for the generation of irregular meters after learning from a dataset of regular meters. Ragtime's straightforward and consistent texture also makes it easier for the model to generalize and learn. For this system's representation, a temporal scope that is a hybrid between time step and note step was proposed to improve that limitation of generating regular meters. It uses the concept of note step and integrates it with a predefined fixed time step. The generation of each note is regulated by reducing or increasing its duration to be a multiple of the fixed time step. For this system, each time step was fixed at 0.25, which means a quarter of 1 beat. Generated notes with duration less than 0.25 were rounded up to have a duration of 0.25. In this case, a note generated with 0.2 duration will be rounded up to 0.25. For generated notes with duration more than 0.25, if it is a multiple of 0.25, it will not be altered. If it is not a multiple of 0.25, it will be rounded down to the nearest multiple of 0.25. In this case, 0.66 is more than and not a multiple of 0.25, and thus will be rounded down to its nearest multiple, 0.50. MIDI was chosen as the symbolic representation of music for this system. For this project, only information regarding a note's pitch, duration, and offset are essential. Other MIDI information such as velocity is not relevant and will not be encoded as inputs. As the hybrid temporal scope representation requires each processing step to be a note, each note or chord in the dataset with the same pitch and duration was encoded as the same variable. For instance, with reference to the picture, a E4 note with duration 1 was encoded as the same discrete integer variable as another E4 duration 1, but as a different variable from E4 duration 0.5. Each unique note with the same duration was first mapped to discrete integer variables, then normalized from 0 to 1. The architecture's flow is as such. An input of 100 time steps with one feature is fed into the first LSTM layer. After a dropout layer, the LSTM outputs enter the bidirectional LSTM layer. The bidirectional LSTM outputs then go through batch normalization and dropout before entering a dense layer activated by the ReLU activation function. The dense layer's outputs go through batch normalization and dropout before entering the last layer of the network. The last layer is a dense layer of size and vocab, where n vocab refers to the number of unique variables in the dataset. The output layer uses the softmax activation function trained on a categorical cross-entropy cost function. The softmax layer outputs decimal probabilities to each class, where each class corresponds to a unique node in the dataset. Moving on to programming language and libraries. Classical Piano Composer from the Literature Review was selected as the starting code for this system. The reasons are as follows. Its current implementation of time-step temporal scope representation is simplistic and can be improved with the proposed hybrid representation. The results it achieved with a LSTM network has room for improvement in terms of structural coherence and content variability. For technical implementation, it has a straightforward and elegant implementation using Python's Keras library. Music 21, a Python toolkit used by classical piano composer, is also a well-documented and supported library with all the necessary methods required for this project's system. Training and generation were both conducted on Collaboratory, a free-hosted Jupyter notebook service by Google. Its benefits include support for different Python versions, free GPU acceleration, and pre-installed major Python libraries such as TensorFlow. After going through the system's design, I'll now elaborate on its implementation. To improve generalization and expedite learning, all pieces in the dataset were transposed to a single key. Pieces with a major tonality were transposed to C major, while pieces with a minor tonality were transposed to A minor. C major was chosen due to its simplicity of having no key signature, and A minor was chosen as it is C major's relative minor. A Python script was written to transpose MIDI files into C major or A minor using library Music 21. MIDI files were passed into stream objects and their original keys extracted. A stream object is a subclass of the Music 21 object and holds information regarding various notation and musical elements of Music 21. A dictionary that maps each original key to the number of semitones required to transpose it to the desired key was then used to transpose the stream object before it gets written into a new MIDI file. The program determines if each note in the dataset is a note or chord object before passing it into a string. For example, a chord object made up of pitch classes C, E, and G would be represented as a string 047. With the input sequence length defined at 100 time steps, each sequence of 100 input notes was used to predict one output note that comes after. This is a summary table of each layer and its output shape. The first layer, CUDNN LSTM, is a GPU-accelerated implementation of LSTM on Keras. Training the model with a regular LSTM layer took more than 24 hours, but replacing LSTM layers with CUDNN LSTM decreased training time to 6 hours. Other relevant hyperparameters can be seen in this table. After 450 epochs, the loss value started to increase due to overfitting. Thus, the model's weights before overfitting occurs were saved and used for results generation. In the generation phase, a random sequence from the input was fed into the model with preloaded weights and used to generate the first output. The output was a set of probabilities for each unique note. The class with the highest probability was appended to the starting sequence and used as the next input to produce the next output. This approach is called iterative feedforward, and the process was repeated iteratively until a sequence of the desired length was achieved. Iterative feedforward counters the limitation of single feedforward strategy, where the length of music generated is fixed by the model's architecture. The desired length of sequence can be defined during the generation phase and is unaffected by the model's architecture. To create a MIDI file from the output sequence, each output was mapped to a note object or chord object, and its duration regulated by a time step of 0.25 as proposed by the hybrid temporal scope representation. These notes were then converted to a stream object and written into a MIDI file. Next, I'll talk about the results and discussion of the implemented system. Results is split into two main parts. The analysis of music generated takes a more technical approach in investigating whether the generated music has characteristics that are aligned with the hypothesis, while the user study uses a more human approach in understanding the audible impact of those characteristics. We'll first listen to a sample generated by the model and analyze it. The score shows that excerpt 1 has both irregular and mixed meters. Irregular meters are circled in red, and the use of multiple meters indicates that the excerpt makes use of mixed meters as well. Regular repetitive musical patterns can also be identified in the phrases marked by blue boxes. Let's listen to another sample. The score shows that excerpt 2 has both irregular and mixed meters. Irregular meters are circled in red, and the use of multiple meters in a phrase indicates the use of mixed meters. Although the phrases may not be as obvious as in excerpt 1, the consistent use of musical patterns and materials can still be identified. For example, the beginning of each bar is marked by a low bass note from bar 1 to 7. The analysis of these two samples show that irregular meters were generated and that the variation and consistent use of musical materials indicates the model's ability to generate music with a good sense of structure and coherence. For the user study, the listening test section consists of 3 excerpts. Excerpt 1 and 2 are sample 1 and 2 that we just heard, while excerpt 3 was taken from one of the pieces from the dataset. The aim of this user study was to verify if people could listen and identify that the music generated by the system has irregular meters, as well as evaluate how its musicality and coherence compares to that of real music. The mean and median response to how rhythmic excerpt 1 was on a scale of 1 to 10 was 6.85 and 7 respectively. 4 participants identified that there was a shift in meter, and 2 identified the use of irregular meters. The mean and median response to the same question for excerpt 2 were 6.46 and 7 respectively. 4 participants identified that there was a shift in meter, and 6 identified the use of irregular meters. The mean and median response to excerpt 3 are 7.95 and 8. Excerpt 3 has a much higher percentage of participants who could identify its time signature compared to excerpt 1 and 2. This is because excerpt 3 has a regular duple meter that is significantly more straightforward to identify. This verifies that participants were able to distinguish irregular meters in excerpt 1 and 2 from regular meters in excerpt 3. This chart compares the scores across all 3 excerpts for how much participants liked them, how melodious and harmonious they were, and how likely the participants thought they were written by a human musician. Excerpt 1 and 2 received very positive feedback. Some participants responded that excerpt 1 had nice articulation, flow, and interesting melody, while excerpt 2 had an interesting descending bass line. Although excerpt 1 and 2 did not score as high as excerpt 3, participants' scoring and feedback was sufficient to demonstrate that the system was successful in generating music with musical sense and coherence. Lastly, I'll conclude this presentation and share some recommendations for this project. In conclusion, a deep learning music generation system with the objective of generating irregular meters with improved coherence was designed and implemented. A new temporal scope representation that is a hybrid of time step and note step was proposed to regulate the length of each note with a predefined time step. A bidirectional LSTM network was hypothesized to allow the network to better learn musical sequences. Score analysis of generated samples and user study showed that the hypothesis was successfully verified by a system generating music with irregular meters and improved coherence. I'll end off the presentation with some recommendations to improve the current system as well as possible future work. Firstly, to increase the extent of human control to make it a more valuable tool for musicians. The current hybrid temporal scope representation has no control over which time signatures to use and when to change meters, as these happen organically and randomly. Secondly, the system could process more features such as MIDI's velocity to enhance content variability and expressiveness. Thirdly, a much larger dataset can be used to investigate how the size and heterogeneity of the dataset impacts the performance of the model. Lastly, deep learning models can also be considered for the task of visualizing music. Thank you.